from the Mediterranean region. And we're going to see the more of it, broader region, also including the Parathetis, and part of that is the Black Sea. And Iouliana VASILIEV will be talking about recurrent phases of drought in the Miocene of the Black Sea region. Iouliana.
Well, when I listened yesterday to the talks, I thought that I'm going to lose you immediately after this title. So that's why I spent a lot of, yesterday evening I spent a bit of time in explaining through slides what I'm going to talk about. Well, about 10 million years ago, it was a big sea over Eurasia, and it was covering important part of this continental margin basically, and that was Parathetis. It was stretching from Austria down to the Aral Lake. This large basin, it was an epicontinental sea, had connections to the ocean via the Mediterranean. And, well, at a certain time, and the people before me explained that Mediterranean was disconnected from the ocean, at that time, Parathetis became disconnected from the ocean too. It was affected indirectly by the Messinian salinity crisis. Well, Messinian salinity crisis, it was an event with no, with no modern counterpart, and this is one of the favorite pictures of many Mediterranean lovers. The point is that here, because of this mountain ridge, the connection between Mediterranean and Atlantic was lost about 6 million years ago. Because of excess evaporation, the water in this basin became hypersaline. Its level dropped down thousands of meters. Deep canyons were incised. And, well, an environmental crisis appeared. And the proofs of this environmental crisis are now well exposed on the shores of the, in Italy, in Spain, everywhere around Mediterranean. There are these very, very thick units of salts. These specifically are gypsum. And it was modeled that you really need, it was, nobody actually knows exactly how much salt is it, because to deposit this amount of salt, you really have to close and open and close and refill the Mediterranean very many times. So only one event obviously is not necessary. You really need multiple refilling of this water basin to reach the thickness of the salt deposited in the Mediterranean. Well, that's going on. It was just a bit too much explaining. Well, and it was modeled, for example, if you are keeping the same parameters of today, like the present-day precipitation and evaporation and runoff, but if you are putting a dam here and close the connection between Atlantic and Mediterranean level will drop down thousands of meters almost instantaneously in a geological time. So in less than 4,000 years, its level will drop down to 1,000 meters. And it will be reduced to a series of very small lakes, a western one and an eastern one. And then if you are going more than, if you are calculating, then in about 2,000 years, gypsum is going to start to be deposited. And when the density and salinity of this water would reach about 10 times the salinity of the ocean, then the salts are going to be precipitated. And that's within 3,000 years. So these events can be extremely fast indeed. But there is something which is never put into all these models, and that's the input of a different water mass, and that's, again, this Parathetis coming from the east. Well, there are some scenarios about this Parathetis. There are two of them. One of them says that at the time of the Messinian salinity crisis, Black Sea had a positive water budget. And because of excess precipitation runoff, it was going and diluting the hypersaline waters of this Mediterranean. Well, another scenario assumes that at the same time, when the Mediterranean was drying out, the Black Sea was drying in the same rhythm, or so, something like that. Well, to know, was it this Black Sea overspilling or was it desiccating, then we need to go and try to evaluate the hydrological balance. You know, this is just a very simple thing. If you are adding more precipitation runoff, the water budget is going to become positive. And if you are adding more evaporation and then much less precipitation relatively, then you are going towards a negative water budget. And this is one of the very, very, very simple equations to solve, because it's just on one side is evaporation, on the other side precipitation runoff. And nowadays, you just measure these parameters. But if you're trying to reconstruct them in the past, I think that these are some of the most difficult parameters to be reconstructed, the evaporation and the precipitation runoff. Yeah, principally because the water involved in all these processes is gone. And then the clouds are gone, the rivers are gone, the evaporation is not known. So you need to play some tricks to trace back the evaporation and the precipitation influence. And this, for example, you have the evaporation. Of course, you have to look at the water as such. And then, well, these are two molecules of water. The essential difference between the two of them is that this one contains a deuterium, which is the heavy isotope of the hydrogen. In nature, there are many more of these lighter isotopes, and a few of these deuterium, the heavy isotopes. And upon evaporation, you are going to extract more and more of these lighter isotopes. And the clouds are going to be relatively enriched in these lighter isotopes. While the basin, it is going to be enriched in the heavy isotopes. Well, the organisms are using these isotopes, the water, and they are going to incorporate the water into their living tissue, into their lipids. So, for example, this is a coccolithophorid test. This algae is producing a specific lipid. It's called a biomarker, and this is an alkenon. The green spheres here are the hydrogens. The black one is carbon, but we are not going to discuss about that, and there is one oxygen. So basically, among these hydrogens, there are always going to be one of these deuterium, the heavy isotope of the hydrogen. And this algae is living in water. There is another way of extracting the signal, and that's, for example, the trees. They are going to store the hydrogen and the deuterium, the light isotope and the heavy isotope, into their leaves, and they are producing leaf waxes. I don't know, I think I didn't lose you all, but the point is that now having these two components, so the sea or the basin and the terrestrial input, we know now that this measuring the hydrogen isotopic composition of the long chain and alkanes produced by trees, you know that you are going to have a reflection of the precipitation. While measuring the hydrogen isotopic composition of the alkanons living in the water, then you are going to have the hydrogen isotopic composition of a sea, for example, Mediterranean. And then you know that, if you are measuring it, you know that if you are going to have a hydrogen isotopic depletion, deuterium depletion, then you are going to assist at a positive water budget. And if you have an enrichment in the deuterium, then you are going to have a negative water budget. So that's basically the method. It's a very new method, and that's why it's not, let's say, it's not yet popular, because it requires some a little bit more work than the commonly used, oxygen and carbon stuff on some other type of fossils. Well, now, I used this method, but I went to the Black Sea, and that's located here, Taman Peninsula, covering Miocene to Pliocene. So I will not talk about the names here, but that's until here, it's Miocene, and the rest is Pliocene. We sampled this section. We analyzed it. Why? Because it is coinciding with the interval of the Messinian salinity crisis from the Mediterranean. And we wanted to know, is it any expression of the Messinian salinity crisis or not into this basin? And we found this terrestrial input, let's say the trees, the tree leaves signal. And we also found this called alkanons that are going to tell something about the basin water chemistry. It's already late. Well, the results are saying like that. Well, on one side, this is the lithological column, schematic one. We have something which is until here is Miocene, and from here on, until here is Miocene, and then from here onwards is Pliocene. We know now that this is coinciding with a Messinian salinity crisis interval with a lower evaporites. Well, what we found out, it was that in these sections, it was a switch in the signal received from the hydrogen isotopic composition. For example, these type of values you are finding in the alkanons when you measure them from the present-day ocean. These type of values, you are not going to find them in the ocean. They are typical more for the for a Sapka type of environment, so very arid, dry, evaporitic, whatever you want to call it. And this switch appeared at 5.8, which is, close enough to the Messinian salinity crisis interval. At the same time, it was a switch in the hydrogen isotopic composition of the N-alkanes. Again, this records the precipitation. And you see that there is a shift from the light isotopes, typical for locations closer to the ocean, and then it goes to much heavier isotopes, lighter isotopes. And this is typical more for, let's say, colder regions or further from the ocean. Well, what we could say it was that indeed, at this 5.8, it was a switch in the hydrological budget from a positive one here towards a negative one, coinciding with this 5.8 and also with these TG20 and 22 peaks, glacial peaks. Well, the conclusion it was that this enrichment in the hydrogen isotopic composition, it must reflect hydrogen isotopic enrichment of the Black Sea, indicating most probably increased evaporation. Well, but the problem is that, of course, we wanted to know, is this just a single event? Is it just because of the location in the marginal part of the basin? And to solve this, I went to the DSDP drilled in the, so from here, I went, well, not here, but I went to Bremen to sample it. And then I sampled the same interval, the presumed interval for the Messinian salinity crisis in here. Well, and the core doesn't look very nice, but it's the only one we have, so we have to use it. And then what we found out, well, there's still a problem with this, because, for example, this interval, by most of the people, it's assumed that it's the Messinian salinity crisis expression in the Black Sea. There is, because here it's a pebbly mudstone and whatever, followed by aragonitic mud and so on. Well, there is a second opinion, less popular though, that this interval, it's actually not Messinian at all. It's just about 3 million years older. So you can understand the amount of confusion this type of correlation would have. But however, we didn't know it at that time, to be honest. So I just went there, hopefully to get the Miocene-Pliocene transition. I went there, and then, well, I found these data. And, for example, we know that these are describing the terrestrial input, and then again, the basin water, and therefore I would have a measure of the hydrological balance. Besides this, I also analyzed a different thing, and that's other components. And then, well, they are telling something about the temperatures on sea and then on land. So I think that you already have a nice set of data to try to work with them. Well, I'll go directly to the data because there is not much time. The point is, I found, again, in the hydrogen isotopic composition of the alkanons on this record, a switch this time from a negative 160 means negative, towards the more positive values, and then towards negative value and towards positive values. It's just like if we want, I would just say that this is negative water budget, this would be positive, this is slightly negative, this is positive. Well, these changes in the hydrogen isotopic composition are always concurrent with some changes in other parameters. For example, the sea surface temperature is increasing extremely fast, from about 8 to 20 at the onset of this sort of marine event. And there are many more, I mean, we can discuss about that a lot. But the point, what I want to say, it is that these changes are also reflected in the palynology. And you also see, again, at the onset of this marine event, you also find an increase in the aquatics in the pollen. And then you see an increase in Macleophorum, which is something that really likes stratification. And then you go to an increase in this Micristidinium that really likes salty waters. So there are really indications of big hydrological changes happening in the region. Well, I will go through it because I already explained that. Well, when we compare these two sites, the northern one with, let's say, the deep sea drilled core, well, if we are putting them together, we see that, well, Taman, that's the land-based section, the first one that I mentioned, well, this dry event could be correlated to this or to the, let's say, to this other one. Are two drying events? Yes. In the DSDP, we record 2 drying events. And then now there is a new work that proved actually that, well, this pebbly mudstone, so the reflection of what was thought the Messinian salinity crisis in the Black Sea, it's not, it's not Messinian at all. It's just something which is much older. And at this level, the top of the aragonitic mud, it's 604. So it is predating the Messinian salinity crisis event. And knowing now this, we can make a guess, and this was the, let's say, the work behind that. We can make a guess, and then that indeed, this lower marine flooding, it's actually correlated well with what's in the DSDP. And then the younger event, this event, can be correlated to the Messinian salinity crisis, but all the older drying event, it's clearly not related to the Messinian salinity crisis. And this was what was thought the Messinian at the time. Well, these are some cartoons explaining what, let's say, what happened at the climax of the Messinian salinity crisis based on the hydrogen isotopic composition of the water. Well, I'll go a bit. How much time do I have?
10 minutes.
Okay. And, well, it was a lot during the climax, so that's during the salt deposition and erosion, you would have indeed a very salty, not salty, a very dry, because it's not necessary to have it salty, a very dry Black Sea. You have a very dry and salty Mediterranean, no connection to the ocean, and huge evaporation taking place. And the point is that this interval from the DSDP is not related to the Messinian, but it's related to something which was actually skipped in the original logs, and it was this interval. When you just have this, you know, very dark layer immediately sharply put onto this rumble of other rocks. And the climax of the older crisis was looking like that, and then most probably this is the expression of this drying event, when the Black Sea had indeed huge evaporation, but Mediterranean was not affected by it. Or some people would call it the Tortonian salinity crisis, but I think I would like to stop with this, I don't know, with this conclusion. Well, so yes, Black Sea was level dropped down 5.5 million years ago, but it was drying out even more before, and that was most probably during Sarmatian. That's actually the 8 million years that you are talking about, when you most probably have the Turkey uplift, and then you have a change in the source of the water from the continents and so on. But that's something that, it's a long story. And learning from this Black Sea experience, when you have this switch between the positive to the negative water budget happening at 5.8, I wanted to know actually what happens in Mediterranean. Do we see the same thing? Can we work with the same methods? And then, well, because, for example, nowadays the situation is very clear. Black Sea, I mean, in the present day, today, we have a salinity of 22, huge influx of fresh water into Mediterranean, although Mediterranean is suffering from extreme evaporation and so on. Well, the situation 5.5 million years ago, it was very different. Black Sea had still, you know, sufficiently fresh water, but Mediterranean was a halite-rich basin, or I don't know how to say that, but you know, few words. And knowing this hydrogen isotopic composition, knowing the hydrological balance in the Black Sea, I wanted to know if I can get the hydrological balance of the whole system. And then, of course, that we need to go to so I showed results from here. I'm going to show the preliminary results taken from Heraclea Minoa. It's a section covering the uppermost salinity part of the salinity crisis. That's the time when they are thinking that it was a sort of lake, or that these are the most ideas. And we analyzed this section, Heraclea Minoa, and we found, surprisingly, this. These are alkanons, are indicators of marine conditions. And that was actually the biggest surprise. I wouldn't expect that. And then we didn't know how to interpret that. But still, you know, we have this data, so we have to work with it. And we measured the hydrogen isotopic composition of these components. And then we found out that, for example, in the gypsum units here, you have indeed these values that are typical for evaporation, which is not a surprise. You know, if you have gypsum, you can expect enough evaporation. So the only thing it is that how these algae were thriving and living in these conditions. And one of the ideas, it's actually that it was brought by, I don't know, some influxes of marine waters or some influxes of water from somewhere else that brought these organisms. So the point is that we cannot explain the presence of this thing. Well, however, at that time it was, again, these are very preliminary results. We have more, but it's like, yeah, we need to plot it in a nice, decent way. And yeah, the Messinian salinity crisis of the Mediterranean, well, it was in a gypsum, of course, with this salinity of 150, then you would expect to have a negative water budget, and that was one of the conclusions. But the point is that, well, to understand a bit all this, we really need, you know, we don't know now what happened in the Black Sea. So I think that to start to solve this box here, the hydrological budget of this box, you really need equal amount of data on equally in time sections, and only then we can start talking about possible correlations or not of these events. And then, well, it went, so there is still a lot of work to be done to understand this Messinian salinity crisis and relation to the Black Sea and the rest. And I would be very happy, I'm not going to use the sword, but I would like to use the balance in trying to understand the events occurring at this region.
Thank you, Iouliana, for a very nice overview. Thank you for that. So, I see quite a few junior scientists in the room. Questions? Not so junior.
Not so junior. I think I missed something in your talk. I did not get when in the Black Sea when you when at the end you said that it was not Messinian but it was dated 6.04 or something. Yeah. Could you just say how you got that date, particular date exactly?
I will try to go fast. With too many animation, I should never do that again. Okay. The point is that, well, this is the date, you know, because like this is Taman section, the land-based section that I showed. Exactly here, you are going to have the influx of Caspidinium rugosum. This was dated using magnetostratigraphy, and I did that in this section, and we realized that the beginning of the C3R reversed polarity is just about here, while this event with Caspidinium rugosum and Galeacista etrusca, it's appearing exactly at 603. In the DSDP, there is also now magnetostratigraphy done on that, but I'm presenting here only the, again, Caspidinium rugosum and Galeacista etrusca, the first occurrence, and this is also about this level. So therefore, if you are having the occurrence of these two species exactly at the same time, and also you get the influx of these terrestrial and aquatics, I mean, this is basically the same pattern. I would say that this is just, well, this is nothing, but for example, here is just a dip, and then here you are also assisting at a dip in the terrestrial influx. So the idea is that this was, the land-based section had magnetostratigraphy and palynology, while this DSDP, and here are presented only the palynology, but we also have the magnetostratigraphy now that is actually proving that this is, again, the beginning of C3R polarity event.
I didn't catch, did you also find N alkanes in the DSTP site or in Sicily? Did you show those to us, or did I miss that?
Show them. Actually, I can show them. Do you know? Yeah, I have actually, yeah, because it was just too much, I think, and I thought that it's, anyway, it's not one thing very easy to digest. We also have these are the N-alkanes. I mean, N-alkanes, if you do not find N-alkanes, I think you should just give up on trying to find something else. So that's just how it is. But we found N-alkanes, and this, we measured the carbon isotopic composition of these components. We also measured the hydrogen isotopic composition of these components. But at that time, we really thought that this is the Messinian interval, so it's much less time involved. So therefore, our resolution, it was not, let's say, the ideal one. And then, for example, for this, it's just, I mean, it was just, we could use the alkanons to spot the switches in the influx of marine or whatever, basinal water. But when you are talking about precipitation, you really have, I think you have to increase the resolution. But however, if you're going, let's say, to this, you see that it's going towards, let's say, there is a swing between, let's say, the more light values, heavier values. For example, this would be more like marine, closer to marine. So, and then you have less close to marine and then close to marine. And then if you really want to see it, you can see that there are changes, occurring at the same levels. When you have, let's say, this is the increase in the sea surface temperatures, And then you get it here with
in the alkanes. Sorry, just to
these are the alkanes,
right? But as I understand, the alkanes should be giving you a purely terrestrial signal, right?
Yes, exactly. Yeah,
and so that shouldn't really be sensitive to sea surface temperature or salinity, right? This is actually what I was trying to get at was how well are you able to separate out the climatic terrestrial signal from simply the water budget?
I think I didn't explain it well then, because this is terrestrial, this is aquatic. So this is Black Sea signal. This is the terrestrial input.
Yeah. But that shouldn't be sensitive to sea surface temperature, should it?
No, but I'm not suggesting that it's sensitive to the sea surface temperature. Somehow, when you see a change in the sea surface temperature, indicating most probably a change in the source water, then you also see a change in the precipitation. And I can imagine that when the surroundings are changing, also the precipitation pattern is changing a bit.
Yeah, but that's what I was wondering if you could get at, is how much of this is a precipitation change versus how much of it is different hydrologic connections within the Paratethys, for example, or to the Mediterranean. Can you really differentiate those?
Yeah, that's why we are using the carbon isotopes. The carbon isotopes are really indicating the source of water. So when you know that you have about 3 per mil shift towards much lighter conditions, then you know, much lighter waters, then you know that there is really a switch in the water source. So it's like, I don't know, either marine or, I don't know, extraterrestrial water, I don't know, it's a joke, of course, but you really have a switch in the source of the basin, of basinal water. This is extra. This is just peanuts, you know. But what the serious problem, it actually relies on the connection between Black Sea and the larger basin.
Question there.
Your hydrogen isotopes are also influenced from the relative height of the mountains and where the precipitation comes from relative to the mountains and so on. Can you comment on that, on how you interpret your data relative to all of this?
Yeah, well, if I'm going directly to this DSDP site, this is in the middle of the Black Sea. So you would expect that the hydrogen isotopic composition of the rain would be close to minus 42, because this railway distillation, it takes, I think, that if you evaporate a bunch of seawater, and then the cloud is going to, the seawater has 0 per mil. The bunch of evaporated water, it will have usually something like minus 36. So these amounts are known, and you can really calculate them. So if you want to translate that in, for example, if you want to translate this in rain received here, you could say that the rain here, it was at about minus 90 per mil. Minus 90 per mil, you get them usually in cold regions or in mountains. But, for example, this one, minus 160, would be translated in something which is minus 60 per mil precipitation. Nowadays, in the Black Sea region, the precipitation there is of minus 60 per mil. So I think you can really get a very good grip on the precipitation going there. And the rest, I mean, the topography and the rest, I think you can also control it somehow with a palynology, because you should have an, I don't know, if you are having an uplift and therefore your hydrogen isotopic composition is affected by the mountain effect, then you would see it in the change in the palynology and so on. So there are ways to control that. But I have to say that this is really at the infancy. I mean, this type of work, it's, well, I think I'm the first one to use at least the alkanons for such a reconstruction in deep time.
Okay, I do want, we are running a little bit late, and I do want to give people the opportunity